Structure of carbon compounds. In 1828, Wöhler, a German chemist, tried to prepare ammonium cyanide in the laboratory by heating together the compounds ammonium sulfate and potassium cyanide dissolved in water. This is a double displacement reaction. When he analyzed the compound, it was found to be different from that predicted. It was urea, NH2CONH2, believed to be formed as a result of rearrangement of atoms in ammonium cyanide. Urea is an organic compound obtained from urine of both human beings and animals by evaporation. It is a white solid. It was the first organic compound to be prepared in the laboratory by chance. It paved the synthesis of large number of organic compounds. Versatile nature of carbon. Catenation. Chemical compounds are broadly classified into two categories: organic and inorganic. Carbon and hydrogen are the two essential constituents of all organic compounds. All carbon compounds, except for oxides of carbon, carbonates, and hydrogen carbonates, are called organic compounds. These are studied under a separate branch of chemistry called organic chemistry. The number of organic compounds known are many times more than the number of inorganic compounds. The existence of such a large number of organic compounds is because of the versatile nature of carbon, which results in self-linking of carbon atoms, called catenation. Catenation is the self-linking property of an element due to which a large number of its atoms can be linked with each other by covalent bonds. As a result of catenation, long chains of carbon atoms are formed, which may be both straight chain as well as branched chain in nature. Examples of branched chain arrangement. Examples of rings of different sizes. These represent only the skeletal arrangement of the carbon atoms. Carbon compounds. Methane is also called as marsh gas as it slowly gets formed in marshy places. Methane is the first member of the family. It is the main constituent of natural gas. In its formation, carbon shares all 4 electrons present in its valence shell with electrons belonging to 4 hydrogen atoms. So, in methane, each carbon is covalently linked to 4 hydrogen atoms by covalent bonds. Next member is ethane. It has 1 more atom of carbon and 2 more atoms of hydrogen as compared to methane. If we look at its structure, it becomes clear that 1 hydrogen atom of carbon in CH4 has been replaced by another atom of carbon. The 3 valencies of this carbon atom have been satisfied by hydrogen atoms as a result of electron sharing. Have a look at electron dot formula of propane. The compounds of carbon and hydrogen, in which carbon atoms are linked to each other by single covalent bonds, C-C, are known as alkanes. These are very little chemically reactive and are called saturated hydrocarbons. These compounds are normally not very reactive. Unsaturated hydrocarbons. Another compound of carbon and hydrogen has the formula C2H4 and is called ethene. Let us have a look at how the molecule can be depicted. Step 1. Each carbon atom gets 2 hydrogen atoms to give 2 single bonds. Step 2. We see that 1 valency per carbon atom remains unsatisfied. This can be satisfied only if there is a double bond between the 2 carbons, giving us the structure shown on screen as step 3. The electron dot structure or Lewis dot structure for ethene is as depicted on screen. Similarly, acetylene formula C2H2 is also called as ethyne. Let us draw the electron dot structure for ethyne. 3 bonds are necessary between the 2 carbon atoms in order to satisfy their valencies. Such compounds of carbon having double or triple bonds between the carbon atoms are known as unsaturated carbon compounds, and they are more reactive than the saturated carbon compounds. Unsaturated hydrocarbons tend to gain hydrogen molecules to form saturated hydrocarbons. Classification of organic compounds. Organic compounds can be of 2 kinds: open chain and closed chain compounds. Open chain compounds are those in which carbon atoms are linked to each other by covalent bonds. Let us have a look at formulae and structures of few saturated compounds of carbon governed by the rule CnH2n+2. Methane has 1 carbon atom and a formula of CH4. Its structure can be represented as shown on screen. Ethane has 2 carbon atoms. Its formula is represented as C2H6 and can be represented as shown on screen. Propane, having 3 carbon atoms, is represented as C3H8. Butane, having 4 carbon atoms, is represented as C4H10. Pentane has 5 carbon atoms and is represented as C5H12. And hexane with 6 carbon atoms is represented as C6H14. Any 2 consecutive members of the family differ in their molecular formulae by CH2. Isomerism in organic compounds. Let us take another look at butane. If we make the carbon skeleton with 4 carbon atoms, we see that 2 different skeletons are possible as shown on screen: straight chain and branch chain. Filling the remaining valencies with hydrogen gives us the following structures shown on screen. We see that both these structures have the same formula C4H10. Such compounds with identical molecular formula but different structures are called structural isomers. We may define it as: isomers are different compounds having same molecular mass as well as molecular formula but different arrangement of the atoms present. Let us take one more example. C5H12 has isomers listed on screen as pentane, 2-methylbutane and 2,2-dimethylpropane. Closed chain or cyclic compounds. A minimum of 3 atoms are needed to form a ring. They can be classified as alicyclic compounds which contain ring of 3 or more carbon atoms and resemble aliphatic compounds in characteristics. For example, cyclopropane C3H6 can have ring structures shown on screen. They have ring structures which differ only in presentation. Have a look at the structural formula, condensed formula and bond line notation of cyclopropane. Let us draw the structure of cyclobutane, that is C4H8. C4H8 forms a square structure with 4 carbon atoms placed at the corners of the square. Each carbon atom is linked to 2 other carbon atoms. Cyclohexane has the formula C6H12 and has the structure shown on screen. In this structure, 6 carbon atoms are joined to form a ring structure. Each carbon atom is linked to 2 other carbon atoms. The remaining valencies are satisfied by hydrogen atoms. Cyclo means a ring and is used as a prefix. Let us draw the electron dot structure for cyclohexane. Straight chain, branched chain and cyclic carbon compounds all may be saturated or unsaturated. For example, benzene C6H6 has the structure shown on screen. Aromatic compounds are cyclic compounds which contain in them 1 or more hexagonal rings of carbon atoms with 3 double bonds in alternate positions. This is known as a benzene ring. Have a look at the structural formula, condensed formula and bond line notation of benzene. Let us have a look at few more aromatic compounds represented by bond line notation. Toluene, ethylbenzene, phenol and aniline. Heterocyclic compounds. Both alicyclic and aromatic compounds have rings of carbon atoms only. These are homocyclic in nature. In heterocyclic compounds, ring may contain 1 or 2 atoms of either nitrogen, oxygen or sulfur as its constituent. These are called heteroatoms. For example, berol, furan and thiophene. Carbon a friend. Carbon seems to be a very friendly element. So far, we have been learning about compounds of carbon and hydrogen. But carbon also forms bonds with other elements such as halogens, oxygen, nitrogen and sulfur. In a hydrocarbon chain, one or more hydrogens can be replaced by these elements, such that the valency of carbon remains satisfied. In such compounds, the element replacing hydrogen is referred to as heteroatom. These heteroatoms are also present in some groups as shown on screen. These are called functional groups. Free valency or valencies of the group are shown by the single line. The functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. Heteroatom chlorine or bromine is represented by functional group halo, which can be represented by chloro or bromo. Its formula can be represented by single bond and chlorine or single bond and bromine. Heteroatom oxygen has the functional group alcohol represented by OH, aldehyde represented by CHO, ketone represented by C double bond O, carboxylic acid represented by COOH. Homologous series. Carbon atoms can be linked together to form chains of varying lengths. Hydrogen atom or atoms on these carbon chains can be represented by any of the functional groups. The presence of a functional group, such as alcohol, dictates the properties of the carbon compound, regardless of the length of the carbon chain. The chemical properties of methanol, ethanol, propanol, and butanol are all very similar. A series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. If we look at the formulae of successive compounds, say CH4 and C2H6, these differ by a CH2 unit. C2H6 and C3H8, these differ by a CH2 unit. Observe the difference between the next pair, propane and butane, which is C4H10. Similarly, let us take the homologous series for alkenes. The first member of the series is ethane. It has formula for C2H4. The succeeding members have the formula C3H6, C4H8 and C5H10. These also differ by a CH2 unit. As the molecular mass increases in any homologous series, a gradation in physical properties is seen. This is because the melting points and boiling points increase with increasing molecular mass.